Part 2 will be weight and balance. A couple of resources for that. Obviously, the reading assignment for this lesson is found in the PHAC, Chapter 10. There's an additional book that you can get from the FA. It's kind of a smaller one. I think it's like 100 pages or something. Aircraft Weight and Balance Handbook. Like I've said before, any FA handbook, you can download those for free. I would say it has more of an explanation into some of these topics that we're going to go into, and also weight and balance applied to different types of aircraft. Section 6 of your POH, also a good resource, and a weight and balance data sheet, which is what I handed to you guys. So, importance of weight. In section 2, you have your limitations, so it's going to tell you your maximum takeoff, landing weight, things like that. The reason why we have limitations is because an overweight aircraft can be an overstressed aircraft. It's going to have a structural limitation. So you don't want to damage the aircraft. It's also going to be, you're going to have a decrease in performance. So longer takeoff roll, it's going to require a higher takeoff speed for the aircraft to even lift off and continue climbing. You're going to have a reduced cruise speed, reduced angle and rate of climb, shorter range. So your en-route range is going to be much shorter. The plane's going to stall at a higher airspeed. And your landing roll is going to be longer. Reason for that, it's much harder to stop a heavier aircraft than it is a lighter one. So we'll get into these limitations. We're going to do a weight and balance example. A standard that you'll want to memorize, because you're going to use this throughout flight training as well as the written test, is the weight of fuel or gasoline is 6 pounds per gallon. So that's just a generic number that you're going to have to memorize. Really common examples you get on the written test regarding the weight of fuel is it'll say you're 60 pounds overweight. How much fuel do you need to reduce in order to be within limitations? So you just divide that 60 pounds by 6, then you get your 10 gallons. So weight is just referring to the total amount in the aircraft. Balance is referring to the distribution or the concentration of that weight throughout the aircraft, in particular along the longitudinal axis. So it wouldn't be helpful to have all of your weight concentrated right here, nor would it be helpful to have it all concentrated right here. So there's an envelope or safe range that manufacturers provide where you can have that weight concentrated in the aircraft, so that way it's stable and safe to go fly. Oftentimes we'll talk about the center of gravity, which is the point which all the weight of the aircraft is considered to be concentrated. So obviously you don't have all the weight in one location, but the point at which it's balanced or concentrated is going to be your center of gravity. So the point at which the aircraft is going to balance. Some terms, I know there's quite a few. It's a good idea to memorize these, especially if you plan on flying commercially. So this is going to be kind of a repeated topic throughout all of your training. At the commercial level especially, understanding what these terms mean, because you're going to be the pilot in command of a commercial flight, and you're going to be expected to understand how weight and balance affect the aircraft, as well as what the limitations are, what the payload limitations are for the aircraft. Most of these applications, like commercial flying, are assuming like small commercial operations. At the higher level, you still have to make important decisions, but a lot of these things are going to be kind of done for you, or using averages is.
They use an algorithm.
Yeah, algorithm.
It's averages for weight.
So standard empty weight, and I'll go through all these, is the weight that consists of the airframe, engines, all items of operating equipment, and that's going to include fixed ballast, hydraulic fluid, unusable fuel, and full engine oil. Most commonly, we're going to use basic empty weight, which is all of these items, but also optional and special equipment. So what that means is anything not on the standard equipment list is considered optional. What that's saying is before you add fuel, so let's say you drain all the usable fuel out of the aircraft, but there's still going to be full oil and full fluids in the aircraft without passengers or cargo. That's what your basic empty weight is. And kind of bouncing off that, unusable fuel. So that's the amount of fuel in your tanks that's inaccessible. So there are low points in your fuel system that you can't access. In an S model Cessna, you have a total fuel capacity of 56 gallons. 53 of that is considered usable. So there's 3 gallons that you can't access or you can't drain from the system. And so that's why unusable fuel is accounted for in basic empty weight, because it's going to be part of the aircraft essentially. Reference datum, so it's an imaginary vertical plane. So if you look at this image to the left, this is your reference datum. It's an imaginary line from which stations are measured. And usually it's going to be in inches from that datum. A couple other ones, your ramp weight. Again, these are going to be self-explanatory. Ramp weight, how much you weigh on the ramp, parked, or for taxi. Same with takeoff weight. More importantly, we look at max limitations, so max ramp weight, max takeoff weight. Other planes will have a larger discrepancy between these two, or bigger kind of difference because they're going to burn more fuel as they taxi. For our Cessna, our ramp weight is 2,558 pounds, and our takeoff weight is 2,550. So 8 pounds of difference, really, because we're expected to burn 1.2 gallons during startup, taxi, and run-up. Useful load, weight of the pilot, co-pilot, passengers, baggage, usable fuel, and drainable oil. Payload, weight of occupants, cargo, and baggage, so what you're adding to the aircraft for the flight. So now getting into the principles about what all these different measurements are talking about. So weight and balance is based off of something called law of the lever. So that's saying that a lever is balanced on the fulcrum, and a force or weight is multiplied by the distance to that fulcrum, and this distance is called the arm. So arm is the distance between the fulcrum and that weight or force. Most diagrams are going to be laid out in the same way, and so anything to the left of the fulcrum is usually subtracted, or it's going to be a negative number because it's ahead of the fulcrum. Anything to the right is going to be a positive because it's added to the distance from the fulcrum. And your moment is the force. It's a rotational force. So in this case, you have a 50-pound weight on the right side being multiplied by an arm of 100 inches. And that's creating a force right here at the fulcrum, a rotational force. And so we're going to learn to calculate that as well. So you want to have this memorized: weight times arm equals moment. Depending on the question you're asked, you may have to rearrange this equation. So sometimes you'll be provided with the weight and the arm. You have to find out the moment. Other times you'll be provided with the weight and the moment only, and you need to measure what the arm is for that distance. So in that case, you just divide moment by weight, and that would give you the arm. So a really common example is a wrench, or if you've ever had to change a tire or use like a large torque wrench or something with a long handle. The reason why you use a larger wrench or longer handle is because the longer the distance, when you apply a force to it, it has a larger moment or larger force applied here at the end. And so when you're trying to loosen a lug nut or work on something, that's very helpful, because if you're trying to use a wrench that's this small and trying to take off a tire on a car, it's pretty hard to do. But if you have a longer handle, it's much easier to do because that force is multiplied by a longer distance. Easiest way to think about all this is actually using an actual arm. So if you think about your shoulder as the fulcrum and you put something in your hand, so I don't recommend putting laptops or iPads. So if you put something heavy in your hand and you put it close to the fulcrum, it's a really short arm. So you can hold this for a really long time. And now if you extend that arm, the weight hasn't changed of the book, but it's multiplied by a longer distance, and sending out feels much heavier on your shoulder. So, don't try it right now. When you get home, maybe play with it. Calculating the position of your center of gravity. So we're going to be using that same formula that we just looked at, except in this case, we're trying to solve for center of gravity. So you take your moment, the total weight, divide those, and you'll get your center of gravity. So looking at this image, here's the datum, which is to the left of the seesaw. Timmy boy is 10 inches from the datum. The center of gravity, or fulcrum, is 60 inches from that datum, and Mary is 110 inches from the fulcrum. So this one, in this example, just the center of gravity happens to be aligned with the fulcrum. That's not always the case. Looking at the table at the bottom, so if we take Tim's weight, multiply it by his distance, that equals 500 inch-pounds, or pound-inches. And you take the weight of the seesaw, which is 50 pounds, and that's 60 inches from this datum right here. That gives you 3,000 inch-pounds, and then Mary, 50 times 110, 5,500 inch-pounds. So you add up each of these columns. So between the kids and the seesaw, the total weight is 150 pounds, and the total moment, or force, is 9,000 pounds. So then 9,000 divided by 150, the center of gravity is 60 inches. So that's why the center of gravity here ended up 60 inches from the datum point. When you learn to calculate weight and balance for the aircraft, you're essentially doing this. Obviously, there's going to be more points of measurement, but this is what you're calculating. You're calculating the total weight to make sure you're within limitations, and calculating the center of gravity to make sure that's within limitations as well. There's a few different methods for calculating your total weight and center of gravity. The first one, computation method, which is most likely what you're going to use for flight training. So that involves adding up weights at different stations, along with the basic empty weight for your aircraft, multiplying that by the arm or station, and then that'll give you your total moment. You do a few calculations, you'll end up with total takeoff weight, total landing weight, and the center of gravity for each of those. So this one's probably going to be the most common for you. Other one is a table method, which you'll be provided. You essentially have to find all of these areas, so like rear passengers, fuel. You find those on the table here. And based off of the weight provided in the example, you'd find out what the moment is at that particular station. This one's going to be a little more common on written tests. You probably won't encounter this very often. Other method is a graph method. So you have a loading graph and a CG envelope. So this is another written test example. Usually in the example, it'll tell you the pilot and the front passenger weigh 360 pounds. The rear passenger weighs 200 pounds. And so the way you calculate that is you trace the black line. So for pilot and front passenger, you follow this until you intersect it with the provided weight. So in this case, it was 360. That's where it hits the black line. You drop straight down. And the moment was 12. And that has been divided by 1,000. So just multiply 12 by 1,000 to get the total. A lot of times they'll abbreviate these numbers so that way it's easier to calculate. And you would do that for each of these. So if sometimes they'll provide fuel in gallons, you just multiply that by 6, or they'll give you the weight of the fuel. So if fuel is 160, where that 160 intersects the black line right here of fuel, and then you drop straight down, a little less than 8.
7.5.
Yeah. These ones can be frustrating. I recommend using a straight edge because sometimes the answer will be something, you just have to find the closest answer to that. Other times they want a very precise answer, and some of the options will be pretty close to each other, and so you have to get out your protractor and like measure as closely as you can to it. Yeah, so I'd say these two are probably the most confusing because we don't practice them a ton. in real life, and they'll come up on the written test. Again, these ones, very similar. You find front seat occupants, the weight provided in the example. So if it said 150, then you'd look at the moment, which is 128. You would add up all the individual weights, all the moments. You can get your center of gravity that way. So the second part of that one, looking at the graph, is once you calculated the total weight and the total moment, is you can take that to this area over here and make sure that total moment is within limitations, and you would plot your center of gravity. So you'd find the total weight and the total moment, and then you'd plot that. As long as your plot is within the envelope or limitations on this graph, then you're good to go. If you plot outside, whether it's above the line, which means you're overweight, or forward or back, you're outside limitations. So let's go over an example. So what you're trying to do is calculate the total weights, the total moments, and figure out the center of gravity. So we'll start going over this one. So for the fuel portion, it provides you with gallons, and you need to convert that to the weight of fuel. So 30 times 6 gives you 180 pounds. And since we know that weight times arm equals moment, you just multiply across each of these rows. Should end up with 24,000 there and 17,000 there. And we can get our center of gravity by adding these columns, so the total weight and total moment. So we end up with 193,000 and 2,055 on this side. So divide those, 193,000 divided by 2,055, and you should end up with answer B. So it says aft, which just means rear. And so remembering back to that diagram, anything to the right of a weight and balance diagram is considered rear or aft. So you're kind of imagining, instead of a diagram, imagine the plane is like this. And so we're trying to measure how far aft or backwards is the center of gravity. So in this case, it's 94 inches aft of the datum. Next, I wanted to take a look at a weight and balance problem that you would typically calculate yourself before a flight. Your instructor will go over this in stage 2 before you begin the cross-country phase. So you have more chance to practice then, but I just wanted to show an introduction to how you'd calculate this before flight and how to ensure that you're within limitations of the airplane before flying. So you would use the information to the left. The basic empty weight, empty moment, empty CG would be provided for that particular aircraft. And then we're going to be using this example. So the pilot or student in this case is going to be 170 pounds. Your front passenger or CFI is going to be 210 pounds. Assuming we're going to have our backpacks, it's going to be 20 pounds. And we're going to use full fuel, which is 53 gallons usable. And assuming start and taxi fuel burn is going to be 1.4 gallons, which you would get from the performance section of the POH. And then we're going to use 18 gallons for this flight. So assuming it's about a little over 2 hours of a flight. And then these are limitations for a Cessna. Max ramp weight of 2,558 pounds, max takeoff 2,550, and max landing weight 2,550. So those will be the same. Looking at the right, this is just an example of a weight and balance sheet that we typically would use to organize this information. Starting off with basic empty weight, you'd get that from the left side here, 1,742 pounds. So we're going to fill in the left side with the weights provided in the example here, and the arm is going to be the weight at each of these stations. So looking at this loading arrangement page in the POH, the front seats are 37 inches from the fuselage station. Rear passenger is going to be 73 inches. The first baggage area is 95, and then a second baggage area is 123. And looking at the notes, so you'll notice it doesn't have any measurement for your fuel station. Down here at the bottom in the notes, it says the usable fuel CG arm is located at fuselage station 48 inches. So now we just need to add the arm. In this case, it's going to be MTCG 41.62. And the moment was already calculated for us, 72,498.83 inch-pounds. Pilot and passenger, this is just referring to the front seats, is going to be 170 pounds plus 210 pounds. So we have 380 pounds multiplied by the station 37 inches, and we get a moment at the front seats of 14,060 inch-pounds. We're not going to carry any passengers, but we're going to put our 20 pounds of bags in the back seat. So we're going to add 20 pounds there. These are separated into 2 different seats. We're not going to put anything else. So we're just going to use 20 pounds, multiply that by 73 inches for the back seat, and we get a moment of 1,460 pounds. We're going to leave the second one blank. So looking at the baggage compartment, just assuming there's always going to be a tow bar or sometimes fuel located in the baggage area A, we're going to add 10 pounds there, multiply that by 95 inches, and we get a moment of 950. Add these all up, each of these columns. You don't need to add the arm, but adding up the weight, and you get a total zero fuel weight of 2,152 pounds. So it's zero fuel weight because we have not yet added our usable amount of fuel yet, so the plane is still kind of light. There's no need to add up the arms at this point, but you do want to add up the moment. And so then we get 88,968.83 inch-pounds. Our next step is to add fuel to this zero fuel weight. Assuming we're going to have full fuel, we're going to add 53 gallons to this spot right here. This isn't asking for gallons, it's asking for the weight of the fuel. So assuming standard 6 pounds per gallon, 6 times 53, we have 318 pounds. Multiply that by the station that we looked at here in the notes, and the fuel is 15,264 inch-pounds. Add these columns up, and then you get our ramp weight of 2,470 pounds. Add up the moment so far, and we get 105,232.83 inch-pounds. Our next step is to subtract any fuel burn for start, taxi, and run-up. So using this amount, 1.4 gallons, which we get from the POH, 1.4 times 6 pounds per gallon, and that gives us 8.4 pounds. So we're going to subtract that in a minute from the ramp weight so far. Multiply that by the same station. So anything with fuel is always going to be 48 inches for a Cessna. We get a moment of 403.2, and then we're going to subtract each of those from the above. So our takeoff weight is 2,461.6 pounds. Moment, 104,829.63. So now we want to get our center of gravity, which is going to be the same as the arm. So moment divided by weight is equal to CG. So divide 104,000 by 2,461. We have a takeoff center of gravity of 42.6. These next spots are called adjusted passenger baggage and fuel weight. Those are in case along your route, if you make any sort of adjustments, dropping a passenger off, adding a bag, dropping a bag off, or adding fuel, whatever it may be. So we're going to leave those next 3 blank and go down to fuel burn. In this example, we're going to use 18 gallons of fuel burned during this flight. 18 times 6 is 108, times the same 48 inches, and we get a moment of 864. And so since we're burning this fuel, we're burning that weight essentially. We're going to subtract this from the takeoff weight. Then we get a landing weight of 2,500, and then we get a landing weight of 2,353.6 pounds. We're going to subtract this moment from the above. We get a moment of 103. We get a moment of 103,965.63 inch-pounds. Moment divided by weight, center of gravity 44.2. So next we need to look at if this is within limitations. So looking at center of gravity limits, we have a total weight, 2,353, right here. We have a total weight of 2,353 right here, and center of gravity 44.2. So where those two lines intersect, we plot a point, and as long as it's within the limitations of the max weight and center of gravity, then this flight is within limitations and it's safe to do. So key weights that we're going to be looking at are ramp weight, takeoff weight, and landing weight. So those are all within the limitations right here on the left, and the center of gravity for takeoff and landing are all within limitations within this envelope. So this flight is good to go. If this plot point was above the envelope, that means we're overweight, or if it was forward or aft, then we would not fly. We'd have to rearrange things or reduce weight somehow if it was above this horizontal line. A few other formulas you could use: a weight shift and a weight change formula. So shift is that if you're shifting somebody from a front seat to a back seat, or just like swapping passengers around, how you can calculate that. This is going to be a little more important when it comes to like your commercial training. This is pretty common for like checkride question. So your weight shift is you're moving somebody in the aircraft and you want to calculate the new center of gravity. So you take the weight shifted, divide that by the total weight, and that'll give you your center of gravity divided by the distance that weight has been shifted. So as an example, top left here. So we're shifting 100 pounds and moving them to different station. So they're moving 120 inches to a new station. So you take the total weight, so the shifted weight, 100 divided by 8,000, and that gives you center of gravity, which we're trying to solve for, divided by 120. That'll give you center of gravity equals 1.5 inches. So it's a positive number. So we're going to add that to this hypothetical starting point of 77. So the new center of gravity is 78.5 inches aft. A weight change, if we're removing or adding passenger or cargo, you take the added weight. In this case, we're adding 140 pounds of baggage to station 150. So 140 pounds divided by the new total weight, which was originally 6,860 plus 140. So 140 divided by 7,000 equals your center of gravity over the distance between the weight and the old center of gravity. So that was 150 inches is where that station, or the new station is, minus 80 inches for the center of gravity. 140 divided by 7,000, center of gravity divided by 70, 1.4 inches. So you're adding that to the original, which was 80, you end up with 81.4. I haven't seen this come up on a private pilot written test, but a commercial pilot written test, you will be asked about this. And so it's a good formulas to practice and memorize. Good to know in general. All right, another common question is this one right here. So how should the 500-pound weight be shifted to balance the plank on the fulcrum? So law of the lever is saying that we're just multiplying the weight or force times its distance or arm, and it should be balanced on each side of this fulcrum. So the question's asking, how should we shift this weight right here, this 500-pound weight, so that way it's balanced to this side, the right side. So we're going to walk through this. You solve these by using algebra. So if you haven't looked at algebra in a long time, which most people haven't, what we do is we multiply each of these weights by their distance to the fulcrum. On the left, we have 500 pounds, and we're trying to solve for the distance. So we're going to leave that blank, and we're going to use that as L. So 500 pounds times L equals 250 pounds times 20 inches, because this weight, 250 times 20 inches, and then the plank, this is the part that's generally confusing for people, is that the weight of the plank is 200 pounds, and you're not measuring these 45 inches at the bottom. We're measuring from the center of gravity of that plank. So since the center of gravity is 15 inches aft of the fulcrum, it's 200 times 15. That will give you, the left doesn't change, so we're going to get 500 L equals 5,000 inch-pounds plus 8,000 inch-pounds, or 3,000, and that'll equal 8,000. So do a little math, 8,000 divided by 500. Length should be 16 inches. So it was originally 15 and it needs to be 16. So which of these answers looks correct? Yeah. So all of this is really just calculating what distance should this top number be, this 15 be, in order for these both sides of the plank to be balanced. And it ended up being 16 inches. So we just have to shift this thing to the left 1 inch and both sides would be balanced. Lastly, I wanted to look at a common written test question you could get based off of the table format for weight and balance. It says, refer to these two figures. What effect does a 35-gallon fuel burn from the main tanks have on the weight and balance if the airplane weighed 2,890 pounds and the moment divided by 100 was 2,452 at takeoff? Our first step is to look at this fuel burn and how much does 35 gallons weigh. So on the tables, we have our fuel table, main tanks. Don't get this confused with auxiliary tanks below that. And the amount of fuel that we're burning is 35 gallons. 35 gallons weighs 210 pounds and has a moment of 158. So first step is to subtract our starting weight and the fuel burn. So starting weight 2,890 minus 210 pounds from fuel. Our new weight should be 2,680 pounds. And if you try and jump ahead, all of these answer choices at a glance look correct. Weight is reduced by 210, weight is reduced by 210, weight is reduced to 2,680 pounds, which is the answer we got. So far, any of those answers could be correct. Our next step is to subtract the moment that we used from fuel. Starting moment, 2,452, which we got from up here, minus 158, which we got from this table. Our new moment is 2,296 inch-pounds. Looking at the table on the right, we can locate our new weight, 2,680 pounds. Number on the left is the minimum moment, and the one on the right is the maximum moment. So you can kind of relate that to the forward and aft limitation for center of gravity. Since our new moment is 2,296, at a glance, you could see 2,296 is greater than the maximum moment limitation right here, 2,287. So up to that point, you can make conclusions about what the answer would be. We're going to take it a step further and look at the center of gravity limitations. Just by dividing this maximum moment by your weight, the aft limit for center of gravity is 85.34 inches. Now, if we do the same for our calculation, 2,296 divided by our new weight, 2,680, we get a new center of gravity of 85.67. So this is aft of the limitation. So you should get to answer A. So just another look about operating at high weights or being forward of your limitation or aft of your limitation. So having a forward center of gravity, you're going to have a higher stall speed, lower cruise speed. Aircraft is considered more stable because it can recover and it's forward of your center of lift. So although you have a higher stall speed, stall recovery is better because the nose is going to be heavier. It's going to reduce the angle of attack. In aft center of gravity, you're going to have lower stall speed, better cruise speed. However, stall recovery is not going to be as great. And that's it. So I'll hand out a quiz, and then if anybody, I know we kind of walked through a few calculations that generally are harder concepts, especially the first pass. If you guys still have questions, just let me know, and we can walk through them.